Consider a simple set S, the collection of all numbers strictly between 0 and 2. What exactly does it mean to be an upper bound? It's simple. Pick a number like 3.5. Is it greater than or equal to everything in our set? Yes, it sits to the right of the entire interval, so it counts. Now, look at 2 itself. Even though 2 is not in the set, because our set is an open interval, 2 is still greater than everything inside. No number in S is bigger than 2, so 2 is an upper bound. But what happens if we go inside the set to 1.5? Can this be an upper bound? No, because there are numbers in the set, like 1.9, that are bigger than it. So 1.5 fails. This means our upper bounds aren't just a single number. They form a massive infinite region, starting at 2 and going all the way to the right. But we aren't interested in just any bound. We are looking for the least upper bound, the smallest possible number in that green region, the tightest constraint. In mathematics, we call this the supremum. Now, let's apply this same logic to the other side. The lower bounds are everything that sits to the left of our set. -1 works. It's smaller than everything in S. 0 works. It is the exact edge. But if you try 0.5, you fail because there are numbers in the set smaller than it. We want the greatest lower bound. We slide from the left, getting closer and closer until we hit the edge at 0. This is the infimum, the greatest lower bound. Now that we have the intuition, let's apply this logic to our broken rational line from the previous video. Consider set A. This set contains all positive rational numbers whose square is less than 2. We want to find the least upper bound of this set. Let's test some numbers. 2 is an upper bound because 2 squared is 4, which is bigger than 2. That's too big. 1.5 is an upper bound. Its square is 2.25, still too big. We can keep finding rationals closer and closer to the edge, but when we try to hit the absolute edge, we crash. The square root of 2 is not a rational number. In our rational universe, that point does not exist. This implies that the set A is bounded, but it has no least upper bound in the rational numbers. To solve this, we need Rudin's formal definition of the supremum to understand exactly what is going wrong. We say alpha is the supremum if 2 specific conditions are met. First, alpha must actually be an upper bound. It has to be to the right of the set. And second, nothing smaller than alpha can do the job. Let's prove this second condition visually. Pick any number gamma that is smaller than alpha. Because it is smaller, a physical gap opens up between them. This is the crucial part. That gap must contain points from our set S. Because there are points to the right of gamma, gamma fails to be an upper bound. This proves alpha was truly the least. The logic mirrors perfectly for the infimum. We say beta is the greatest lower bound if it bounds the set, and if nothing larger, then it works. Visually, if you try to pick a gamma to the right of beta, a gap opens up again. Points from the set live in that gap. So, gamma fails. Beta is the true boundary. We will use this exact logic to define the real numbers. We don't define them as points on a line, but as cuts. We define the square root of 2 not as a number, but as the cut itself, the boundary where the supremum of the left set meets the infimum of the right set. That meeting point is the real number.